Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our session of Q&A. So in this session we're going to talk about 3 different chapters by 3 different people, okay? So we're going to have chapter 3, chapter 5 and chapter 7, correct? Yeah?
Yes.
Alright, so let's start with chapter 3.
Okay, what I'm going to talk about is memory hierarchy and cache for chapter 3. Simple. Okay, first I will explain memory hierarchy. Memory hierarchy is the arrangement of different types of memory based on speed and size. The closer the memory is to the CPU, the faster and smaller it is. For example, registers and cache are very fast, while main memory and storage are slower but larger. Next, I will explain direct map cache. In direct map cache, each block of data from main memory can only be stored in one specific cache line. If 2 data blocks map to the same cache line, one will replace the other, causing a cache miss.
Okay, that's all. So I have a question, right? You mentioned about memory hierarchy, correct? How does that work?
Okay, first of all, this diagram shows the memory hierarchy. At the top, we have registers, which are the fastest and smallest. Below that are level 1, level 2, and level 3 cache, followed by main memory and secondary storage. As we go down, the memory becomes lower but larger.
Okay, thank you. That was chapter 3, yeah? Okay, so let's talk about chapter 5, which is machine level representation of a data. Basically, computers don't understand words or numbers like we do. They only understand on and off, which we write as ones and zeros. First up, number system. We use decimal, base of 10, every day, but computers use binary, which is the base of 2 that contains 0 and 1. To make binary easier for humans, sometimes we use hexadecimal, the base of 16, or octal, the base of 8, as shortcuts. Next is positional notation. A digit's value depends on where it is. In decimals, places go 1, 10, and 100. In binary, they go 1, 2, 4, 8, 16, and so on. Now, integers. Unsigned numbers are just positive, but for negative numbers, computers use signed representation. The most important one is 2's complement, because it lets computer handle negative numbers and subtraction really efficiently. What about decimals like 3.14? That's where floating point numbers comes in. Computers use the IEEE 754, which is kind of like scientific notation. It stores a sign, an exponential, so it can handle really big or really small numbers. Finally, binary arithmetics. Computers mainly do addition, even subtraction is done by adding a negative numbers using 2's complement. This makes the hardware simpler and faster. Okay, so that was it from my explanation. Any question?
Yes. So, how do you find the two's complement of a binary number?
Alright, bet. To find the 2's complement in a binary number, just follow 2 simple steps. First, flip the bits, changing every 0 to 1 and every 1 to 0. This is also known as finding the 1's complement. Second, add 1 to the result. After you flip the bits, you add 1 to the result. That's it. Alright, clear?
Clear.
Alright, so that is chapter 5.
Alright.
Let's move on to chapter 7, yeah?
In chapter 7, we will discuss about parallel processing. It's easy. So basically, this chapter are discussing how computers improve the performance and efficiency of a system by using multiple processors. Things that we need to know in this chapter are multiple processor organization, symmetric multiprocessor SMP, multiprogramming, and multiprocessing, and Amdahl's law. First of all, multiple processor organization. Multiple processor organization is a computer system that uses more than one processor. The main goal is to improve speed and performance by running tasks at the same time. Secondly, symmetric multiprocessor SMP. It is a system where all processors are equal. They share the same main memory. A single operating system controls the system. Any processor can execute any task. The advantage of using SMP is faster performance and simple design. Thirdly, multiprogramming and multiprocessing. So what's the difference of multiprogramming and multiprocessing? Multiprogramming use only one processor. Multiprocessing use multiple processors. The CPU in multiprogramming switch between programs. It appears parallel but not truly parallel. In multiprocessing, the tasks run at the same time. This was the real parallel execution. For example, in multiprogramming, single-core CPU running many applications. Multiprocessing are using multi-core CPU to run the applications. So that's all in chapter 7. So
Okay, I got a question too. You have mentioned about Andan's law. Is it right?
Yes.
Okay, I want to know what is that.
Oh, in Amdahl's law, it states that the non-parallel part of a program limits the overall speed up. For a simple example, 50% of a program can run in parallel and the other 50% must run sequentially. Even with many processors, the speed up is less than 2 times. Just like that. Easy, right?
So that is it in our Q&A session. I hope you enjoyed this video and I'll see you guys next time.